In this section, we're going to jump into our first 3D coordinate system that's different from our Cartesian coordinate system. So we're going to talk about cylindrical coordinates. Now, realistically, this is just the 3D extension of polar. So not much is going to change from when we were working with double integrals and polar coordinates. The only difference is now you have this third component, which is just going to stay our normal z. So to show you what this system actually looks like, here is our 3D system. So we've got x, y, and z. What happens now is every single point that we plot is still determined by a triple. Normally it's x, y, z. The z coordinate is going to stay the same. Nothing is going to change, except x and y are going to switch over to r and theta. And the way we switch over is the same way with polar. So our x coordinate is given by r cosine of theta. The y coordinate is given by r sine theta. And your z just stays put. So there's still the same connection between x and y. If you do x squared plus y squared, it's still going to be the radius squared. Okay? So the way we plot these is a little bit different. If you remember in polar, what we would do is we would plot the angle first, and then we would use the radius. If it had a negative radius, you shoot through the pole. So here, we're always going to go through, and we're going to plot theta first. So theta goes out in this direction. Then we have that r value that tells you how far out to go from the origin. So r to here. And then this would be that point in the xy plane, r theta. But now we add the z component, so we just travel up that distance of z. And in this case, this is going to be the absolute value. It's going to be positive up here, the length of this side is. Because if you're going down, then that length would be negative. Right? So let's try to just plot a couple points in here, and we're going to work at looking at some of our common shapes that we've been dealing with in these cylindrical coordinates. And then we'll talk about how do we deal with triple integrals with this. But again, the z is just staying put. You're switching over x and y the same way we do for polar. So all of the same conversions still work. But let's try an example of just plotting a point. So plot the point whose cylindrical coordinates are (4, pi over 3, and negative 2. Once we plot it, then we're going to find the rectangular coordinates. For this point. Okay. So if we want to plot this, our radius is going to be 4, our angle is pi over 3, and then the z coordinate is negative 2. All right, so let's get our xyz plane going. So starting with that angle, I have to go pi over 3, which is 60 degrees. So starting at that positive side of the x-axis, I go forward 60 degrees, which is to right around here. Then I need to go out a distance of 4. And again, I'm kind of guesstimating. Let's say this is a distance of 4. And that would lead you to this point here. And now my z distance is 2, but it's negative. So this means I'm going to drop this down 2. Okay. So our point ends up all the way down here. This is 4 pi over 3, negative 2. When I go to switch over to rectangular, the only thing I really have to find is x and y, because we have z already. Since our x is given by r cosine of theta, the x is 4 cosine of pi over 3. pi over 3 is a 60-degree angle. It's in quadrant 1. So cosine of pi over 3 is a half. So this becomes 4 times a half. So my x-coordinate is 2. My y-coordinate is given by r sine theta. So that's 4 sine of pi over 3. And then sine of pi over 3 is going to be root 3 over 2. So the same kind of thing happens. The 4 and the 2 simplify to 2. So the y-coordinate is 2 root 3. So this point in rectangular coordinates is given by x, y, z. It is 2 root 3, and then nothing happens to that z coordinate. It's still negative 2. Okay. So one thing you're going to have to kind of be conscientious about is if you're given a triple integral just in general, you might have to figure out what is the best way to set things up. And so cylindrical is really nice when you have one cylinders. They're great for cylindrical. But also if you have stuff that's circular in the x and y direction. So we're going to go through and we're going to show how to set things up potentially in all of the coordinate systems. So what does it look like in rectangular? What does it look like in cylindrical? And then when we get to spherical, what would the setup look like there? And then based on that, you kind of can pick which one is easiest. That being said, you want to be comfortable writing everything in each of the coordinate systems, okay? So you might not be evaluating in rectangular coordinates, but you still need to be comfortable setting up some integral with those rectangular bounds, okay? One of the biggest things that you need to be comfortable doing is drawing pictures here, because that's going to make or break some of these problems. So let's try some examples. We're going to identify the surface. So we're going to be given it in cylindrical coordinates. And we want to figure out what does that surface look like. So z equals 4 minus r squared. I want to get this in rectangular coordinates so I can actually graph it. And in that case, I know what r squared is. So we replace r squared by x squared plus y squared. And so that minus sign just distributes out to everything. And if you remember what kind of shape this is, it's an elliptic paraboloid. Totally okay if you don't remember that name. But if I want to graph this, I'm going to go ahead and look at all of my traces. So we'll start with the xy trace. So in that case, you set z equal to 0. So you get 0 equals 4 minus x squared minus y squared, which gives you a nice circle of radius 2. So we'll graph this one in pink. Looking at my next trace, let's do the xc. And there we set y equal to 0. So you end up with a parabola opening downward. And this one we'll draw in blue. Then finally, we've got our yz trace, which is very similar to the xc. So it's 4 minus y squared, also a parabola opening downward. Okay. So I can use all of these to get a really good picture as to what's going on. Because again, graphing is very important for us. Also going to graph the back half of these. Try to make it as even as possible. We don't need to do the z downward though, as long as we have the top half. Okay. So in our xy plane, we have a circle of radius 2. So we'll do our best to draw that, even though it's at an angle. And so here is one half of the circle, and then you have the back half of the circle. So that's x squared plus y squared equals 4. Then if I do my XZ trace, that is a parabola, and that 4 tells us the largest value for Z. So if you plug in x equals 0, it goes through Z equals 4. And then it's a parabola opening down. So it comes to here, and then we've got the back half, which we'll do as a dotted line. Okay. And then we've got the same in the YZ plane. Goes through 4 at the top and then comes downward. So that is our elliptic paraboloid. All right. Let's try another one of these. We'll identify what kind of surface it is, and then we'll also graph it. So let's do 2r squared plus z squared equals 1. And again, for this one, if I want to get this in rectangular coordinates, which is nicer to actually work with, I'm going to go ahead and change that r squared over to x squared plus y squared. So this is 2x squared plus y squared plus z squared equals 1. So really what you end up with is that ellipsoid. So I have equals 1 on this side, which is good, but the problem is I need something underneath the x squared and y squared to tell me how much in each direction I go out. I don't like that 2 next to it. So instead what I do is the same way as saying 2 times is it's x squared divided by a half, because you multiply by the reciprocal. This is y squared divided by a half, and then z squared is divided by 1. So this gives us that ellipsoid. You absolutely are welcome to find the traces, but it's really just like drawing an ellipse, because you would have an ellipse in every single direction. So what's underneath each of these tells you the distance you go out. So you take a square root. So in Z, you go out a distance of root 1, which is 1. And here you go out a distance of root 1/2. So that one's not super accurate, but that's okay. So we'll still draw a little picture. We're just going to go out less in the x and y direction. But it is uniform because we have a circular in the xy plane. So I'll draw all of our pieces. And then we'll go ahead and make those negative components dotted. Okay. So the biggest distance is again in my z direction. So I'm going to start by drawing my big ellipse in this direction. In the xy plane, I have a circle. So we got the front half and then the back half. And then in the XZ, same thing. So that is our ellipsoid. Okay. So what we're going to do now is we're going to talk about using cylindrical coordinates when we get to triple integrals. And this again is going to be really useful when you're working with stuff like cylinders. Spheres are they're okay, but they're better for spherical coordinates. You're going to see that some of these are not great once we get to spherical. But at least in these first couple examples, you're going to see the benefit of having a different coordinate system, because if we were to use rectangular, it's going to be atrocious. Okay? But in general, to use cylindrical coordinates for triple integrals, we have the following. If you want to take the triple integral over some region E of a function of x, y, and z, and then you're going to integrate with respect to x, y, and z in whatever order. To make this simple, typically what we end up doing is we do dz, and then this order doesn't matter as much, dy dx. Because I'm really just extending this as a third direction of polar, all I'm going to do is change over the dy dx. So the solid will still give you some kind of bounds. Depending on what's in the inside, all of the x's you replace by r cosine theta. All of the y's you replace by r sine theta. Z you leave alone. But now remember what happens with polar is the dy dx switches over to r dr d theta. So you're going to get an extra r in here. dz does not change. And then you integrate with respect to r and theta. So these switch over exactly the same way. Okay? So basically what you're doing here with cylindrical is your dv is going to switch over to r, dz, dr, d theta. So for these next two examples that I'm going to do, we're going to work with a pretty common shape that you're going to see in our next section as well. And this will also appear a lot when we get to our vector calculus sections. So it's basically what I like to call an ice cream cone or a snow cone. Snow cone is probably the better word for it. So for these two examples, you're going to see we have two surfaces. So we're going to find the volume of the solid. E, that is bounded above by z equals the square root of 2 minus x squared minus y squared. And it's bounded below by z equals the square root of x squared plus y squared. So again, to be able to find my bounds on these things, I have to be good at getting a drawing for this picture. So I want to start by drawing each of these things. So beginning with the lower bound, the z equals the square root of x squared plus y squared. This is a cone, okay? If you look at your traces, the xy trace would be 0 equals the square root of x squared plus y squared. This is that boring case. It just gives you the origin. If you look at the xz trace, this would be z equals square root of x squared. So it ends up canceling out, but remember, it gives you absolute values. And likewise, if you look at the yz trace, it would be z equals the square root of y squared. So you get an absolute value in that direction. And because the xy trace was useless, let's go ahead and figure out when z equals 1 what the shape looks like. So it gives you 1 is the square root of x squared plus y squared, which gives you a circle. Okay? So in the xz and yz directions, we have these sharp absolute value functions that look like this. But then in the xy direction, we have circles. So this creates that cone. For this other shape, this hopefully looks familiar at this point. If you set this equal to 0, you would end up seeing that you have basically a sphere. Kind of we've been working like y equals the square root of 2 minus x squared minus y squared. Because of this being z equals the square root, you know it's greater than or equal to 0. This is basically not a semicircle, it's now a hemisphere. So it's half of the sphere. And specifically, it's got a radius of root 2. It's basically the square root of whatever this number is. So just to show you, if you squared both sides, when you move the x squared and y squared over, you have that sphere, okay? But because of the way it's written, it's just the top half of the sphere. Now, basically, because I'm utilizing these two surfaces, it's below the sphere and above the cone. One thing that's going to be important to find is to figure out, what do these two things intersect at? So we also need to find the intersection of these surfaces. So all we do in that case is we set the two things equal to each other. So we've got the square root of x squared plus y squared equals the square root of 2 minus x squared minus y squared. Squaring both sides gets rid of those square roots. And then I'm going to go ahead and group the like things on one side. So if I add the x squared and y squared over, we get 2 of everything. And then dividing by 2 gives us a nice picture that this is a circle of radius 1. But I also need to figure out the z value it specifically happens at, so I know where they intersect is a circle of radius 1. But for what z value does that occur? Well, we can really use either of these, but this is the cleaner one. Since z is equal to x squared plus y squared, and x squared plus y squared is 1, z is going to equal 1 at the intersection. Okay? So we've got everything we need now to get a good picture. I'll try to draw this a little bit bigger. Okay. So we've got our first cone, and I should probably draw the back half of these to make it a little bit easier. Make these dotted. We've got our cone. So z equals the square root of x squared plus y squared. You have an absolute value in each direction. I'm just going to draw this version of it. So this is z equals square root of x squared plus y squared. Then it's going to intersect with this hemisphere. So I'm going to draw the intersection that we just figured out. This is z equals 1, and x squared plus y squared equals 1. And then sitting on top of that, we have that hemisphere. And the biggest it goes is root 2. So this is z equals the square root of 2 minus x squared minus y squared. Okay? So my goal is to find the volume of this thing. Now, because I'm just specifically looking for the volume, I can also use symmetry to my advantage. Because this is a snow cone, I can find really what the volume is in the first quadrant or octant and then multiply it by 4. However, if I'm dealing with evaluating a triple integral and these are my bounds, I can't necessarily do that, okay, because I don't know that the inside would be symmetric. But here, since I'm specifically looking for the volume of a solid, we can find the volume in octant 1, multiply it by 4. Again, what I want to do is I want to get comfortable setting this up in all of my coordinate systems. So cylindrical is going to work pretty nicely for this, but I do want to set it up in rectangular coordinates. So if I'm going about thinking of how this goes, my z coordinate is probably the easiest. So your z value is always going to start at the bottom of the cone and go up to the sphere. So my lower limit is going to be the cone. My upper limit is going to be the sphere. What I need to do then is figure out what is going on in the X and Y direction. And that's really where this intersection is going to help us out. This is the biggest the X and Y coordinate is ever going to go. So what's going on in the XY plane is we're really integrating over this unit circle. So this is going to help us figure out the bounds on X and Y. So this is essentially our region of integration. So what I'm going to do is, again, I'm going to find the volume just in this first octant and then multiply it by 4. So I also am going to get a good picture as to what's going on in the XY plane, because I need this to set up my bounds. Okay. So we've got a circle of radius 1. So I was like drawing my circle first and then filling in the pieces. So this full circle is x squared plus y squared equals 1. And I'm going to worry about just this quadrant 1. So we're going to use symmetry and find the volume here. Then multiply by 4. Okay. So we're going to set this up first in rectangular coordinates. But you can see, because we have a circle in the xy direction, cylindrical is not going to be bad here, because I can switch everything over in terms of r and theta much nicer. So you're going to see how awful this would be to actually integrate in rectangular coordinates. Doable, but it would be rough. So to find the volume of any solid, it's a triple integral over this region E, which is just the cone. And then you put a 1 on the inside and integrate with respect to x, y, and z in whatever order. So I'm instead using symmetry and multiplying by 4. And then I want to figure out what are the bounds for this first octant. And again, this is going to make sense to do dz. The other ones don't matter, but typically dy dx is good idea. So starting with the z bounds, we again are always going to start at the bottom of that cone and go up to that hemisphere. So our lower bound, wrong tool, is going to be the square root of x squared plus y squared. And the upper bound is the square root of 2 minus x squared minus y squared. Now I want to figure out what's going on in quadrant 1 in my xy plane, so we need the bounds here. The easiest bounds are the last one, x. In this case, our x is going to change between 0 and 1. Now for the y value, that one's a little bit more difficult. Let's see, what color haven't I used? I can use yellow. Our y value is always going to start at 0, and it's going to go up to the edge of that circle. And it's the top half of the circle, so if you solve for y, it's the square root of 1 minus y squared, or x squared. So our bounds for y are 0 to the square root of 1 minus x squared. So you can do this integral, but again, it's not going to be pretty, and it would probably require some kind of trig substitution within it. So instead, because my x and y are circular, I'm going to set this up using cylindrical coordinates. So our volume is still the same thing. It's a triple integral over E of dV. And I'm going to use symmetry to my advantage. Set up all of these bounds. The thing I have to remember, though, is when I switch to the dV, you get that r dr d theta. So you get dz dr d theta in this case, since we have that z component. Hopefully you can see these two aren't super hard to change over. So in the first one, you can factor out that minus sign, x squared plus y squared. This upper bound becomes the square root of 2 minus r squared. The lower bound here, in that case, you would take the square root of r squared, gives you the absolute value of r, but it really just becomes r in return. Okay. To just show you this off to the side, we've got this upper bound as the square root of 2 minus x squared plus y squared. So it is 2 minus r squared. The lower bound is the square root of x squared plus y squared, which is the square root of r squared, which gives us the absolute value of r. But again, we're always going to assume this radius is positive for us. Okay. Now all I need for the r theta bounds are to look at my circle. I'm dealing with a circle of radius 1, so my r bounds are 0 to 1. And then I'm only focusing on quadrant 1 because I'm using symmetry to my advantage, so my angle is 0 to pi over 2. So this is very, very, very nice because I end up having these constant bounds, and that's fantastic. Okay. So before I can go about breaking things, though, I've got variables inside my z, so I do need to go through this integration with respect to z first. But thankfully, since the inside does not have z at all, the antiderivative is just r times z. And then evaluated from r to the square root of 2 minus r squared. Okay. And since these are z bounds, we just replace z by that. So we end up on the inside with r times the square root of 2 minus r squared, and then minus r times r. Okay. So super nice. So I'm just going to ultimately rewrite that as r squared to save myself the hassle. So now this is really nice. This is a separable integral because this inside has absolutely nothing to do with theta at all. So I end up having to go through the integral from 0 to pi over 2 d theta. And then unfortunately for r, I do have to split this into two integrals because I can integrate r squared easily, but this one I'm going to have to make a u sub on. Okay. At this point, if you're comfortable just knowing that this is pi over 2, great. I'll show you that it is, but typically our theta bounds are always going to be 0 to some constant with a 1 on the inside. So it ends up just being this top bound. Basically, you're finding the area of a rectangle of length 1 out from 0 to pi over 2. So I'm going to go through this first one. This becomes theta evaluated from 0 to pi over 2, which just becomes pi over 2 minus 0. So you see it just takes on that constant. Now over here, I don't really want to do like a u sub inside of this. So what I like to do is I like to show my work off to the side. So I'll kind of put a bar to make a separation so it's not super messy. We want to integrate from 0 to 1 of r square root of 2 minus r squared dr. So my substitution that I'm going to make is my u is going to be 2 minus r squared. Du is negative 2r dr. I don't have that negative 2, that's not a problem. Just bring it over as a negative 1/2. And then for our limits, we definitely want to go through and do those. And let's even move these over so I don't take up as much room. When r equals 0, our u is going to be 2 minus 0 squared. When r equals 1, u is going to be 2 minus 1 squared, so it becomes 1. So this becomes negative 1/2 the integral from 2 to 1 of square root of u du. Okay. And then if you don't like that the bounds are out of order, remember that minus sign can cancel with that. You just flip the bounds. So now we've got 1/2 the integral from 1 to 2 of square root of u, which is u to the half. So going through, we increase that power by 1. So that gives us 3/2. Divide by the new power, which is the same thing as multiplying by the reciprocal. And then that's evaluated from 1 to 2. So this becomes 1/3 u to the 3/2 evaluated from 1 to 2. Which gives you 1/3 2 to the 3/2 minus 1/3 1 to the 1/2, or 3/2. So we've done that integral completely. So this becomes 1/3 2 to the 3/2 minus 1/3. Okay. And now I need to go through this integral, and that one's much nicer. Bump the power up by 1, divide by the new power, and then this gets evaluated from 0 to 1. When you plug in 0, it does absolutely nothing. So that's 1/3 times 2 to the 3/2 minus 1/3, and then really minus another third. Okay. At this point, you can clean stuff up a little bit if you would like. 4 divided by 2 gives you a 2. So this ends up equaling 2 pi, and that's 1/3 2 to the 3/2 minus 1/3 becomes minus 2/3. You can factor out 1/3 if you want. If you left it like this, perfectly fine. You might see your answer as this instead, though. Okay. So this is the volume of that snow cone. Again, this is going to be a pretty common shape that you're going to see because it can work in all of our different coordinate systems. I'm just going to do one more similar one, but a different looking sphere. Instead of a sphere of radius root 2, we're going to look at a sphere of radius 1 and see how can we set up the volume for that. But the integration would be very similar, so I'm not going to sit here and go through that process again. It really just changes the constants slightly. But just so we can get familiarized with this. So for our last example, for cylindrical for now, again, we're going to do it when we talk about spherical too. We're going to set up the volume of the solid. Enclosed by the cone. Which is z equals the square root of x squared plus y squared, and the sphere x squared plus y squared plus z squared equals 1. You might also notice some other cones in your homework and all. What basically you could do is you could input a constant inside of here. So it would basically just change a different particular angle, which we'll talk about in spherical. but the same kind of idea for cylindrical. So if I were to graph these, it's the same kind of shape in both of them. So I'm not going to bother with the traces because we've already done that. So working with our sphere, we'll start with our cone. Looks like this. Set z equals the square root of x squared plus y squared. Then we've got a sphere of radius 1 sitting on top. So again, has that ice cream cone shape. And it's still going to have a circular intersection. I do need to figure that out because that plays an important role in what my bounds look like in the xy direction, because we're just going out a circle. So let's find what is that intersection. So I'd have to first go ahead and solve this for z, so then I could set it equal to this one. So z squared is 1 minus x squared minus y squared. I can go ahead and take the square root, but realistically I can also just say from here z squared is x squared plus y squared. So setting these two things equal to each other gives us that 1 minus x squared minus y squared is x squared plus y squared. Moving those over, we end up with this. And I know it's some kind of circle, but I need x squared plus y squared by itself. So bring over the 2. So this is really a circle with a funky radius, which is the square root of a half, or 1 over root 2. You can rationalize this if you want, but absolutely no need to. So this intersection is x squared plus y squared is equal to a half, and specifically you could figure out what z value that occurs for, because x squared plus y squared is a half, so z is equal to the square root of a half there. All right, so I want to go ahead, I'm going to do this time just setting it up without using symmetry to my advantage, because again, if this wasn't just finding a volume, if I had a function on the inside, I could not use symmetry. So what I need for my volume is a triple integral with a 1 on the inside. I'm not going to set this up in x and y. Instead, I'm going to immediately just do cylindrical. So it's r dz dr d theta. My z is going to go, see, here's my tool, from the bottom of the cone up to the top of the sphere. So again, just switching those over. Z is the square root of x squared plus y squared. So it's square root of r squared. Those r squared and square root cancel. And then we don't have to worry about absolute value because we're assuming r is a positive quantity. For the other, I need to solve for z squared. So it's 1 minus x squared minus y squared. So z is just the square root of that. And you can factor out that minus sign to see the upper bound is 1 minus r squared inside a square root. Now to figure out my r theta bounds, that's where we're using this intersection here, which is a circle of radius a half. If you want a picture of that in the xy plane, absolutely feel free. So that's x squared plus y squared equals 1/2. And this time again, we're going to use this entire thing to figure out our angle. We're starting at 0 and going all the way around the circle. So the bounds on theta are 0 to 2 pi. And then here for the radius, you're starting at 0 and going out to the edge of the circle. And in that case, the radius of the circle is 1 over root 2. So again, this is very similar to the last example to actually integrate, but good practice to get more setup. So make sure you are drawing a good picture for these. It is going to be very helpful for you.